Paul Kinsky. I've been writing Haskell for a little bit, a couple years now, full-time, hobby before that. So this talk is going to be about Merkle trees, and specifically how they're used in distributed version control systems at first. So it will be building on what I introduced in the last two sessions, where I showed you how to just do a simple diffing algorithm. And we'll be building on that by essentially just making it more robust, and showing how you can actually take advantage of some properties of Merkle trees, like specifically using the hashes on each node to actually do an efficient diffing algorithm, right? Like the kind of thing that actual production distributed version control systems like Git and Merkele do. When, for example, you have a 1,000,000 file repo and you only want to diff the subtree of it that's changed. So let's just recap for a second, right? Merkle trees, it's a tree. Each node is tagged with the hash of the previous nodes, the child nodes. So if you have some data blocks, this is from Wikipedia, by the way, the data will be tagged with its own hash. A node that has a pointer to the leaf node will be tagged with a hash of its contents plus the hash of what it points to, so on all the way up the tree, right? Nice tree-type structure, perfect for Haskell, right? This has some really desirable properties for, especially for distributed web stuff and for just version controls, right? Because every bit of structure is tagged with its hash. You can use the hash as a key for caching. You never have to do cache invalidation. You never have the key or the value pointed to by a key changed. So that's pretty nice. You can also do really easy diffing of trees. So imagine you have this whole tree, right? And you change just this. So this would have its hash change, this would have its hash change, this would and this would. But this entire subtree would have its hash remain the same. So let's say you have tree 1 and tree 2, right? Tree 2 is after you've made that change, and you want to diff the two. Imagine this is a repository. You're diffing two states of your repository to get the change Git style. So you would be able to skip diffing this entire subtree. You wouldn't even need to descend into it, because you just compare the hashes, you'd know they were equal. And you'd just be able to descend into this tree. So that's really nice. It means that the actual amount of work you have to do for diffing two trees is proportionate to not the number of things in the tree, but only to the number of changes. And that actually sort of makes it feasible to diff large Merkle trees, like 1,000,000 file repos and such, as used by various big Gos. Right, so number of files changed, but also if there's changes in a directory, yes, it's proportionate to number of files changed. So this is really great. You can use it to represent directory trees, but you can also use it for commit graphs, commit trees. You can use it for, say, if you have a BitTorrent, everything in BitTorrent uses Merkle trees. It's just not a tree really, just a list of hashed objects, but still, that gives you really good properties for distributed systems. IPFS uses it. Every blockchain project, blockchain is a Merkle linked list. I mean, you can use both. Yeah. They're sort of orthogonal in what they do, but good question. Yeah, so before I dive into the specific type of Merkle trees that we're working with, does anyone have any questions? Cool. So what we're actually interested in working with here is directory trees. And this doesn't have any of the hashes or anything. It just has the structure that we're diffing. So you've got a top-level unnamed directory, as in Git, right? Your top-level directory in Git is never named, or in Merkurial. And then you've got a bunch of pairs of path and file tree entities, and that represents the entities in every directory, right? Those are either files, and we've put the body of the files inline in here. In an actual system, and I have a repo that's a fully worked example, in an actual system, you would have a reference to the hash of the files so that you can avoid grabbing the full file contents and just grab the hash of the file to compare. And then to get a directory tree to actually work with this, you actually sort of recursively stack these layers using fix of directory layer. So that's one of the main things here is the combination of Merkle trees in this sort of fixed point representation as used in recursion schemes. So, recursion schemes, right? The basic idea is you can generalize over fold and unfold in the same way that like, a for loop generalizes over using gotos to zip around between locations in code. And it gives you sort of a similarly powerful abstraction, right? So all you really do is you have a fixed point of some functor, and then you just sort of recursively stack that functor on top of itself using fix. It's a type level fixed point. And to fold, you only have to write a algebra to fold a single layer of the fix. And notice that A doesn't have to show up anywhere here. And to unfold, you just have to write an algebra to unfold from a seed value into a single layer. And then the actual recursion schemes, abstractions, the recursion schemes machinery, handles chaining that. It handles the recursion. Like, you don't actually have to reference the actual recursion in your code. You just have it handle it for you. Similar to how if you're doing for loops, you don't have to reference the actual jumping back to the beginning of the loop with a goto. So I'm just going to treat those as sort of magic functions that we have access to for this talk, and I'd be happy to talk to you more about recursion schemes, but this is mostly going to be about how to use them and not like the underlying stuff, but to help you build an intuition. So imagine you have a tree that you're unfolding, right? So this is an anamorphism. So you start with some seed value, you apply that coalgebra once, and you get like a tree, and that tree ends with seed values, and you just keep applying it repeatedly. Each time you unfold layers, you're just doing that, right? And eventually you hit a terminating case, which is, I guess that's going to be a square here, and you stop unfolding. But it's also very good at producing infinite structures. So it's some care is sometimes taken to make sure you know when you have an infinite structure and make sure that you're okay with dealing with that. And then with a catamorphism, if you want to consume this, right, you just need to write something that, this is, yeah, perfect. Write out the layers with this. You just need to write something that consumes a single layer. So you'd write something that goes from this just to some value, and then you would substitute these recursive links with those values. And then you'd fold up each layer here to the next value, and you just keep each layer here to a value, which would be used to substitute the recursive links in the next layer. And you just sort of keep doing that, right? And eventually you get to the base of it, and you've folded everything below the base up into just these values, and then you just fold the base up into a value. So that's sort of, I hope that provides a bit of intuition into how catamorphism and anamorphism work. I'll have some more examples with like really simple fixed points as we go through this. But essentially, you can treat those as magical functions that help you generalize over this stuff. Without knowing how the underlying abstraction works, it just works because it compiles. That's how we know. Right. So we're going to just go through some really simple examples of recursion schemes over like simple layers, and then we're going to show how we can compose the layers to get like interesting structure, streams where it's interleaved with like I/O so that you can like lazily construct more, just all kinds of cool stuff. Right. So first, simple functor, one of the simplest functors, right? Tuple. So if you have a tuple A, B, you have a functor that applies over the second part of the tuple. So you have a functor over a partially applied tuple. And you can build an infinite stream with this, right? So look at what that would look like. You have a fixed point of that tuple. And if you, like, I've actually written a version that uses an anamorphism and a version that just does the recursion manually, so you can sort of see the difference between them here. So you're just doing it manually here. Imagine you have a fixed point of that tuple, and then for the first value, you're going from some integer, and you're just sort of expanding that infinitely, just infinite list style, because Pascal's lazy, we can do that. So you have your n, say n is 0, then from called with n plus 1, you fix, etc. And yeah, so you build out an infinite stream using this. You probably wouldn't actually do this. You just define your stream type, but this will sort of help build intuition as we build up more complex things that actually do things that you do require recursion schemes to do in an elegant way. And you can see here it uses an anamorphism. The only real difference is instead of manually recursing by calling back to from, in from tick, it actually just uses an algebra that builds out a single layer of it. So you get a stream of integers with like n, and then you just get like the next like seed value that you unfold from with n plus 1. And then the anamorphism actually handles repeatedly applying that to just unfold out, in this case into infinity, but you could easily imagine something like this that has a terminating case. Not with that functor, but with something. Any questions while I have this on screen? Cool. Try and slow down a bit. Yeah. So another simple functor, right? Maybe. Everyone's familiar with how you can fmap over maybe? Cool. So you can use it to represent piano numbers, where you just stack the numbers inside each other. You stack the maybes inside each other, and nothing is 0, right? 0 is just the terminating case. And then every time you want to get the successor of a number, of a nat, right, which is just a fix of maybe, you just stack another fix of just in front of it. So neither of those are really useful as so much. You wouldn't really, these are just sort of intuition pumps, but we can actually get a sort of useful type if we compose them, right? Is everyone here familiar with a functor composition? Cool. Just really briefly, functors compose for free, which is just a nice property, as do traversables. You just have a new type wrapper over 2 functors, and it'll just let you fmap over the internal A for free, right? You don't need to chain fmaps. You can just chain composes and do a single fmap over the whole thing. So that's pretty cool. What do we actually get out of this, right? Why do we actually care? So let's say we want to build a list with compose, right? We can compose maybe and a partially applied tuple. Sorry, that should be a partially applied tuple of int, because I've specialized that to an int list instead of a. But we can, here, we've defined, this would be a list of int, right? And I add the tick to it because in the previous talk, I used different formulation of a list of ints, and I wanted to distinguish between them. So just to make sure we understand, or just to make sure it's like legible, I guess, there's an example here where we have a simple list of just like 1, 2, nil, right? So your console is just, right? You hit just, you know that there's more structure that's similar to a console. Because you've already hit just, you have to also have a tuple, as you do here. So you have a tuple of 1, and then you're up here, so you loop back to the beginning of the fixed point. Then you have fix, again, compose of just and tuple, or of maybe and tuple. You have your next console, right? You have your 2. Then you loop back through fix and compose again, and you have nothing, right? That's equivalent to nil. Does that all make sense? Cool. I actually kind of like that you can build up a lot of like common recursive types just from these like couple primitives, like either and maybe and like a few other things. It's an interesting property. Actually, I'll get to that in a second. Just to make sure that we have some examples of catamorphism. You can actually, again, that should be int instead of a there. You can actually fold using kata, which generalizes over folding. You can fold over a list of ints and produce like an actual Haskell list of ints. And what you're doing is you're taking the functor type that's inside the fixed point, and you're collapsing that with the assumption that every subsequent layer has already been collapsed down into the value you want to get at the end. So if you have compose nothing, that's nil, right? And if you have compose just some tuple and then like the accumulator for what you've already folded down, you just, you're turning it into a list. So you take this element, you take the rest of it, and you just, you compose or you combine it using a console. So, I mean, it works in the, works in the REPL. And yeah, I mean, you can turn my list, which is 1, 2, nil, into a Haskell list of 1, 2.
But how do you do that recursion on the accumulator?
Sorry?
How do you do that recursion on the accumulator?
That's the cool part. Catamorphism does it for you. You don't need to actually do the recursive call yourself. Like if you were writing this yourself, you would, just like using primitives, you would explicitly call toList here, or like you would be like x:2list rest, right? But you don't actually have to do that. You just define something to collapse a single layer of it, and the catamorphism handles doing all the bookkeeping for you. So it's similar to that with an anamorphism, and you can actually see that these definitions are very similar. They just flip the algebra around. Like, oh, did I? Oh, Jesus, sorry. This should actually be from list of int to int list f of int, yes. Sorry, I added the type annotations just last night just to make sure I have them. Yes, so you can see here it's taking sort of the same logic, just going between the two types, where if you have an empty list, it's just compose nothing, because that's the equivalent to nil. And if you have head and a tail, it's just compose of just, that's your con cell, the head, and then the tail. And as before, the anamorphism handles actually recursing for you, because you don't need to actually build out the whole recursive structure in your algebra. You just need to build out a single layer of it. And then it's with the recursive parameter substituted with just a seed from which you can unfold more structure. Right. So far, like, we've defined a list, and this is actually something kind of cool that I saw Iceland Jack put on Twitter, but you can actually define a non-empty list by just flipping the order of it, a non-empty int list, right? If you have the tuple before the maybe, that means that as soon as you get your fixed point, you have to have at least one element, right? You have at least one tuple, and then you have the opportunity to have just or nothing. So in that case, we've actually just flipped the composition of the two and changed the meaning. And the reason why I'm referencing the Iceland Jack Twitter thing is because the idea is, like, you know, which is more complex, which is more simple, non-empty list or list? They're actually as complex as each other because they both have the same components that go into them, just in a different order. Thought that was kind of cool. And you can see, like, just a simple non-empty list, right? You have to have that tuple on the outside. There's no way to make it empty, just structurally. Does that all make sense so far? Anyone have it? I might be zipping through this a bit fast. If anyone has any questions, that's, yeah, awesome. So we can do that same trick with trees, right? Where instead of maybe, you have either a and list. So, right, you're going through this, right? So you'd start with a node that's, if it's a left, that's just a leaf, right? It doesn't recurse anymore. But if it's a right, that means it's going through the compose to list, and you have some number of children. And then back to the fix, and so on. You either have a leaf or a node with more children, and et cetera, right, through the tree. Now, just as with list and non-empty list, if you actually just, like, flip the order of these two, you get a different type with sort of the equivalent of the difference between list and non-empty list. You get a forced, right? Because right at the top level, you have the opportunity to have an empty list. You can have an empty forced, or you can have multiple unrelated trees there. Right. So big part of why that's there is that, you know, hey, maybe that looks a little bit familiar, because the directory layer is sort of a weird formulation for a tree. Normally with a tree, you have the node at the top instead of the list of nodes. This is sort of just a forest of subdirectories, right? And as with Git, you can have an empty forest of subdirectories that you start with as, like, an empty repo state. So here's how you would actually write a directory tree just using fix of, like, for lack of a better word, primitive functors, as in things that exist in base. Like, you start with the list, right? That is the directory layer entity list. Then you have compose for the next level. You have it tupled up with a file path, which is here. Everything in the list has a first element that's a file path. And then compose again. You tuple it up with the either. That gives you the branching between the file body and the recursive case, which is the subdirectory. And then you zip all the way back up to fix. You keep going down that as long as you have subdirectories. Yes? It's something I made up because you can't really do type equality, probably. Yes, excellent question. The tilde equal equal is just a sort of, like, shorthandy, like, hand-wavy pseudocode sort of way of saying that these types have, there's an isomorphism between the two types.
Right. You could probably
Sorry?
You could make it actual quick check test by using type representation from type bubble or Dir Tree.
Ooh.
And check that because actually generics encode the thing with the similar way, except that there is no explicit fix. Instead of explicit fix, you have the constructors, right?
Yeah, this is kind of similar to generics, right? Because you can take your recursive type and just break it up into things that exist in base already, like sort of like list and either and a few others. And you can actually build pretty much any, I mean, I would say any recursive type. I would love to hear counterexamples later, like, but yes, I'm asserting that you can build any recursive type using this technique out of just stuff in base. So let's actually get a fun example of that, right? You can actually make stuff, you can interleave layers of I/O into your structure. So let's take the stream from before. And instead of an infinite stream that has to all be there concretely when you construct it from pure functions, let's make it so you run each layer in some monad before you get that structure, right? So simple example of what that might look like. And again, something you probably wouldn't use in prod code, but something that's useful for sketching out the concept is if you want to just successively read lines from standard in and parse them to integers, and you want to build a pure value that represents the act of doing that, you can build a int stream parameterized over I/O, because every time you fetch another layer of it, you're doing I/O, as just a, sorry, the type of this is, again, wrong. That should have an arrow to int. No, sorry. No, it should be int to that, yes, because it's a unfolding and not a collapsing. And you can see here, it just builds like a compose of I/O and tuple, with the next layer just being the next int from which it unfolds, the next int that gets printed to the screen when it requests a new integer. So this is actually going to be critical for working with Merkle trees, this sort of interleaving of actions with a recursive structure, which is why it's here. So we can make a lazy directory tree where you have some monadic effect interleaved between every directory layer. And you can see a simple example of that here, right? We're just constraining it on some monad so we get pure, just for the sake of this example. I mean, it could be applicative, but it doesn't make sense unless it's in a monad, really, for purposes of actually doing stuff with it. So you have fix, you have your monadic effect. You should also have composes in there. I did not put composes in there. Sorry, there should be a compose between fix and pure in both of these cases. But you can see how you construct a simple example of that. But that doesn't actually get us anything, really, because it makes it lazy and we can lazily traverse it. But to actually do stuff with it, we need to be able to look at the hash of every Merkle tree layer so that we can compare them, that we can maybe decide not to dereference them, etc. So what we want to actually do is build this structure. We start with a tuple. That's the hash that we're going to unfold to get the next layer. Then we interleave that with the monadic effect that we actually do the unfolding, the fetching in. And then we compose it with the directory layer that we're actually fetching. So this lets us, if we have 2 trees, this lets us look at the hash of any subtree before we actually dereference that hash and grab the subsequent structure. Because sometimes we can just look at the hash and know we don't need to actually grab the structure. All right, I'm going to show you how to build these here. Does anyone have any questions? Cool. So this is what it actually, again, you have the lazy Merkle directory tree M. And all you really need to do to build one of these is provide a function from some hash, which is just a SHA-256 cryptographic hash of the contents, to the subsequent directory layer parameterized over hash, right? It's a function that just gets you one directory layer from a store. And all you really do is you just stack some composes around that, like with anamorphic algebra or coalgebra. So you have your hash, you compose the tuple with the hash with the actual action, which fetches the hash layer and the hash, right? What's kind of cool about this is that you can build a lazy Merkle directory tree from anything that gives you this function, right? So you could have a local file store where you're reading stuff off of, like, say, JSON encoded files there. You plug that into there, right? You get a lazy Merkle directory tree of, say, IO, or accept TIO with your actual error type if you're trying to be actually doing good code. And if you want to fetch stuff over the network, you can use servant. There'll be some examples of these different types of directory stores in a little bit after I get through the directory tree specific layer, because you can actually build all these stores and all these abstractions as generic sort of tooling that can work with any F and not just a directory layer. And you can also just have testing, right? Like, you can imagine the monad is identity, because I mean, in this case, for IO ref, it would have to be IO, right? But it could be identity if you have everything spec'd out already. It could be STM. It could be just like state T if you have a map inside the state T that you're actually grabbing stuff from. And each of those would work, right? So you can build a lazy Merkle directory tree several ways. And what's cool is then you can write functions that work over any lazy Merkle directory tree with any M. And I'll show you that in a second. So we're going to actually try and diff two lazy Merkle directory trees. And the reason I was saying that a second ago is it's kind of cool, right? All you know is it's a monad. Like, you don't know anything. It's not monad IO. It's not like monad some capability, monad reader, etc. All you know is that you have the ability to sequence actions in some M, like literally nothing else. And you have two, sorry, these should be lazy Merkle directory trees, not lazy Dir Trees. Yeah, and then you just produce in that same monad a list of diffs, where the diffs are, you know, a simple enum type of a file modified, file replaced with directory, directory replaced with file, entity deleted, and entity created. And this is a stub right now, just so we can get all the basic type signatures on the same page. And each diff is also going to be tagged with the file path at which it occurred. Does that make sense so far? Cool. If you were at the last talk, this should actually look very similar. All we've really done is add an M parameter to everything, because it's now happening in a monadic context instead of just with a fully substantiated, fully fetched directory tree. And again, actually, this slide's basically the same, because in the case where an entity is removed or it's added from either, right, you don't actually need to do anything. You're just like, oh, the entity's been deleted if it exists in the first tree but not the second one, or vice versa, if it exists in the second tree but not the first one, it's been created, right? And then you just have the path tupled with the diff, and you don't actually descend into the file tree entity. So this can just be X, right, instead of Dir Tree as it was last time. This case is slightly more complex, where you're diffing to directory trees. You're handling conflicts, right? So in this case, you have two file tree entities at the same file path. And they're backed by lazy Merkle directory trees. Sorry, that should be, should have added the Merkle parameter to that. And yeah, all you do is a couple cases. You have a conflict, right, at that single path, and something's been replaced from between a file and a directory. That means the file's been replaced with a directory, or vice versa for a directory to file. Or you have, say, two file entities, right? And then you compare them. And in this case, this is with the sort of simplified formulation where you actually have the file contents inline, which you wouldn't really do. But you'd actually do the exact same comparison between the file hashes, which allows you to only look at the directory structure and not the potentially quite large file structure. Right. So far, this is really, yeah, basically just doing some pure functions, wrapping the results in pure because they're not doing any actions. The only really actions happen in the this, if there's a conflict, right? If there's a conflict between subdirectories. So you have two directories, they're in some way different, they're at the same path, and all you really do is you recursively call back to diff directory trees with directory entity 1 and 2. And then that's a monadic action, so you fmap over that and fmap again, just to prepend the path that you're at. So you sort of build up this list of diffs in there, and then you prepend the path at which the diffs occur to them to build up the full path. Right. Then really just putting it all together, you don't really have to do much. All you have to do is, as before, we're using the map merge utilities and just the containers package. They're excellent. They handle all the bookkeeping for us because we have a list of tuples of file path and then of key and tuples of key and value, right? Tuples of file path and file tree entity. So you can just convert a list of key value tuples into a map very easily in Haskell. That's sort of the naive representation of a map, is that list of key value pairs. So you just convert them, do from list for both, and then you apply on removed or on added in the two cases where something's missing from one or the other, and you do on conflict in the case where it's not. So this is actually once you've already dereferenced them. So what you're doing at the start, right, you have your lazy Merkle directory trees, 2 of them. You know you're in some monad, but you literally just know you're in some monad. You don't know anything more than that. And so you have your compose, outer compose, then your tuple with your #1 and #2, and you can just compare the hashes, right? If the hashes are the same, you know that nothing changed because, yeah, like if the cryptographic hash of some content is the same, we're basically discounting hash collisions here because this is the sort of thing where if you run a computer the size of the moon for the age of the universe or something, you might be able to find them. But like in practice, I think it's like really non-trivially hard to even like get them theoretically. So yeah, so you compare the hashes. If they're the same, 0 work needs to be done. And we don't descend into the structure in which we've interleaved actions with layers of the structure. But if there is a difference between the hashes, we now know that we have to descend into the structure, right? So we actually dereference via the 2 effects inside the compose. We dereference directory layers with entities 1, entities 2. That's our key value pair list, right? And we plug all that into merge. And we're using merge A here, which is basically just mapping 2 merges, but using functions that can actually run in a monadic context to handle the merge conflict resolution. And then, yeah, then we just grab the elements from the map, which is our list of diffs, and we join them together because then we have a list of diffs, which isn't what we really want. And yeah, we get a merge res, which we return and either recurse on or have that be our final bit. So let's actually run this, right? Like, let's show it off in the REPL. Once again, I am using Windows. Please be gentle. Everything's on a Linux subsystem. Yes. So we're just going to read a single repo. We're going to read a single repo in one state, get a hash for it and everything, then make a small change to it, and then read it again. And it'll just work. So I have a, is this all showing? Mostly, yeah, it cuts off the corner, so yes, that's good. And so we have just a temporary file store in /temp/file store that I'm using. So we're just going to nuke that. And hgit. Hgit is the actual repo in which I sort of built like a fully worked version of this. So we're just going to read the sort of clean state on the refactored branch, right? So that gets us 1 hash, right? 66C, et cetera, et cetera, et cetera. And let's change something, right? Like I have all the actual non-pure IO-ish code in here. So let's, I don't know, echo foo to a file called bar. I've been doing that a lot while I demo this, but you know, it would work if we hopped into an editor and made some non-trivial changes too. Yep, modified. So then we just grab it again, right? We read the directory tree again, and then we write it to a directory store, or a local file-based store by consuming it, which under the hood uses a catamorphism, which is kind of cool, but you don't really need to know that, right? It's just this magic set of abstractions that helps us out. So you can see the hash has changed, right? Because we've changed something in one of the files. Like we've changed something all the way down here. So that changes the hash of this, changes the hash of this, changes the hash of this, all the way up. So the root hashes are different. So now we can just construct, and this is kind of cool, right? These 2 lazy Merkle directory trees, This is both in let, right? These are pure functions. We're not actually doing any work at all to construct them. We're constructing them totally purely. But it's only comparing them that requires doing work. And if the top level hashes are the same, it wouldn't even need any work to do that. Yeah. So let's actually diff them, right? And we created a file. It was like called foo or something, contents bar, doesn't really matter. But we should get a single diff for that at the path, right? hget axt app runtime bar.hs. We've created that entity. While I've got this open, does anyone want me to play around with the repo a bit more? If anyone has some specific type of change they'd like to see if it breaks it?
Just a question. You say like it's just doing the effect whenever you do the diff, right? But you actually define the values, then you make a change, and then you define the other value, right? So you have to do some kind of storage, right?
Oh, it has to do the work to actually read the thing. But excellent question. So this is monadic, right? It's reading a directory tree from disk. It's just like repeatedly calling, like enumerating the elements in a directory and recursing on them. And then this is monadic. It's folding that tree up, hashing each layer, and writing it to a store. But once we have that hash, we can construct a lazy Merkle tree from just that hash, and we can do that as a pure function. But there's, see this? So I did modify it. I created that like foo.baz or whatever in between reading it the 2 times. And these are both I/O actions, right? They both actually reference the outside world and do some stuff, which is, which they kind of have to, right? Because they're reading from the directory. But actually just constructing the 2 lazy Merkle trees as a sort of pure value with I/O interleaved between the layers. Since the I/O is interleaved between the layers, we only really need to do I/O when we take a layer and unwrap it. We don't need to do I/O to construct that.
And this is why it needs to be a monadic effect. You cannot do an applicative effect, right? Because you need the dependency.
Yeah, because you don't know the structure of all the applicative actions just at the beginning. Let's go back a slide. You actually need to you actually recurse into this, and based on entities 1 and entities 2, you may or may not be recursing, right? Like you get a different answer from the initial monadic query, and that changes the structure of computation. So that doesn't fit into an applicative frame. So before I move on from diffing, does anyone have any more questions or examples they'd like to see? Cool. So last time someone actually asked me if there were some where we'd construct a tree instead of just constructing like a list of values or something. So this little interlude is going to build up to that, right? If you're familiar with free or co-free, and here you'll see this like weird tilde == type notation. Again, right? You can actually fix of either A composed with F is equivalent to free of F of A, right? Because you either have pure or free at each level, and then you have F, and then you recurse into the sort of fixed point style. Same with co-free, right? You always have something at the beginning, that's your tuple, and then you compose it, you have your F, which is here, and then you have your next co-free that's sort of equivalent to fix. And I was thinking that might help build intuition if you're familiar with fix and, or if you're familiar with free and co-free, but not with fixed point representations. But partially that's here to be able to show this, right? So we're going to be doing a lazy merge of 2 directories instead of a lazy diff, which means that we don't actually descend into the whole thing. We just descend into the bits that we know have changed and build up new structure. So what this is doing, right? This is the kind of type we want for the result. We're actually taking fixed point of either, that's the equivalent of free, right? Like we know if we hit the lazy Merkle directory, there's like some sub-branch that the hashes were equal for, so we have no need to recurse into it. Or we have a directory layer, and the directory layer is newly created structure. So the reason for this, right? Imagine you're merging 2 things, and also imagine that you're kind of lazy, so you didn't want to put together merge strategies. You just want it to fail if there's any merge conflicts. So you're going to create like some new structure as you go through that. Like you're actually going to perhaps create like some new directories when you notice that there's like 2 subdirectories, one that exists in A, one that exists in B. You need to merge those. So how that would sort of work, right, is either you sort of upload those newly created structure as you go through, but then maybe the merge fails and you've uploaded some stuff that you don't care about that's trashed now, and you've like done network I/O for no good reason. Or you sort of don't upload it, and then you risk someone messing up when they actually use the resulting value and thinking you've uploaded the new structure, but not. So this actually encodes at a type level that there's like a difference between the pre-existing structure and the newly created stuff. And what this actually does, right? So this is yeah. So this is what merging actually looks like, right? And again, there's no knowledge about the actual monad stack. You just know you can sequence actions in it. And here we also have, this is from like the actual HGit repo and not the sort of simplified version. You have, oh God, sorry, yes, of course. Thank you. Is that good? Yeah. Cool. So you actually have, instead of the file type, you just have some x, which you know how to compare equality for. And you have two lazy Merkle directories again. And then you just either get like a merge violation or a merge result, which is the type down here, where it's either your lazy Merkle directory, subsequent directory structure, or just another dir layer. Yeah, so this time we're not even like handling the missing case. Like if missing just means that something exists in one map but not the other, and that's just, if it's a merge, that's like a clean merge. You can just do that easily. But if there's a conflict, right? If something, and this is just the historical path, right? The path at which you're at. This is the actual path of the two entities. You just, you compare them, they're equal, the merge succeeds. If not, you throw. And with directory entities, you just like, again, you either compare them, you know they're equal, and you just return the full lazy Merkle tree, or you just have, yeah, you just merge the directories, going back up to the top case here. So I'm not going to go through all of this, but it's just to point out that you can use this sort of, so someone actually pointed out that there's something called like a zippomorphism that sort of generalizes over this. I don't know what that is, and the name kind of scares me, so I haven't really used it yet. But it's entirely possible that you can generalize over the sort of similar functions for merging Merkle directories and diffing them using something like that. Right. Yeah, so actually, I'm going to hop over in this a little bit. It's actually kind of cool. You only have a couple core things in here. It's like a couple hundred lines to define like the core abstractions for like a Git or Mercurial style distributed version control system, and then a couple like same for diff and merge. And these are the actual types that we end up using, or that I end up using in my thing. And there's a bunch of annotations up there, some capabilities. And this time you actually have a list of blobs, and I've changed it to a tree in one branch of this because a linked list of blobs is a bit weird, but whatever, right? So that you can actually have very large files with the ability to like sort of paginate and grab successive layers of structure and have like a hash of them. And then you have your file tree entities, and here the file entity is parameterized over like what the files look like in here. In that case, it's just the hashed subentity or the directory. And again, you have commits, which use a sort of similar thing, right? It's parameterized over a couple things. You have a commit root directory, right? And that's just a hash of a Merkle directory. Or you have the commit parents, which is just a hash, a list of hashes of subsequent commits. And there's a bunch of bookkeeping here with the extract keys and stuff that I'll go over soon. Yes, probably in the next talk. Yes, so in the next part of this, I'll be going through the actual abstractions you can use to work with generic Merkle tree type things and to build your own sort of systems that use this sort of same lazy unfolding and like a couple other abstractions which work for any Merkle tree type system. Like you can, there'll be like file stores, network stores, property tests for them, and etc. that are all parameterized over, instead of directory layer specifically, instead of any F that has a couple type class constraints. We are getting up to 3:20 now, and that's the 15-minute mark. So I'd like to give a chance to ask any questions.